Welcome back to Calculus 2. We are talking about numerical integration, the ways in which you could program the computer to solve more difficult integrals. So in the last section we saw that there is a list of integrals in a textbook. It contains 106 different versions of integrals with their solutions, and we can compare the integral at hand to whatever is the same in that list, and then just read off the answer. Now, numerical integration is there for the problems that are not in that list. So that list is finite. It has 106 integrals in it, and that's it. We would like to explore what happens if the integral that we are dealing with is not there, and if we would like to write a software for it, right? All of the computer science majors are now happy in this classroom. You want to write a software piece or a program that would compute this. In some sense, the two most rudimentary techniques for this you already learned in your Calculus 1 class. The left-hand sums and right-hand sums that are studied at the beginning of Chapter 5, right when the integration was introduced, are the ones that you guys already should know. I will briefly remind you of it. So if you have some kind of a function, and what you do is you divide the sections like this, and then let's say you are using right, let's use left. You're using left corners to create these rectangles. Rectangles will have the width of delta x, and they will have the height of the function computed at the x value plugged into the function, right? So your function is always given to you, so you know what that is. You have all of these partition values that you get. The first one is always called A, the last one is always called B, and N is the number of rectangles. And delta x has the formula B minus A over N, because we are definitely dividing the entire interval with the number of rectangles to get how wide each of the rectangles is. So now when you have this particular situation, and this is all in Calculus 1, you are supposed to know this or be familiar with this at least, we say that the area is approximated by simply multiplying, well, adding all of the individual areas. Let's do it one by one. So we have f of x0 times delta x plus f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x. So these are the values, and now you can just, using basic algebra, you can pull together all of these f of x0, f of x1, and so on. Times delta x at the end, factored out. Now this quickly turns into the Riemann sum by writing these f's as the summation, and then we send that number of rectangles to infinity, which means their delta x actually shrinks down to 0 and so on. So there's a lot of cool stuff that's happening here, and all of this turns into, so you learn that in your Calculus 1. Today on the menu we are talking about three methods that are used. That is the midpoint rule, trapezoid rule, and Simpsons rule. So those three rules, they all have the formulas. You will use those formulas. They're all like this: addition, subtraction, multiplication. That's technically all it is. So let's start immediately with midpoint. I will draw exactly the same picture, and we are going to divide it into these smaller regions. There we go. And now the word mid, right? Midpoint, well, rule, midpoint rule or whatever. So midpoint, what do I do for a midpoint? I will go in the middle of each of these delta x's, and I will find the middle and use the middle to draw this horizontal line for the triangle. And in each one, for the rectangle, sorry. So for each one, I'm going to do the same thing. So I'm not going left, I'm not going right, I'm going exactly into the middle. And now if you pick any one of these, I'm going to color one of these. So let's say this one. You see the purple? You see that on one side, I am overshooting the area. On the other side, I am undershooting the area for about approximate amount. They're not the same. It's not the same amount, but it's close enough. So whatever you add as extra and unnecessary on one side, you will subtract about the same amount on the other side. Observe how precise, how much more precise that is than what we had in the earlier case, where in this particular case here, everything was error. 100% of it was error, right? So clearly the true area in this case is smaller than what we approximate using just algebra, right? Well, in the midpoint rule, it's very, very close. So now you still have your x0, x1, all of those. The first and the last are still called A and B. Your delta x formula never changes throughout any of these methods. That will stay forever. That will never change. So now the only thing that we want to do is we want to come up with a formula that will compute all of this. So what you are clearly doing is you are figuring out the midpoint between x0 and x1. So now area is approximated by, and we're going to, you know that each one of these rectangles will be tan delta x. So I'm just going to, let's do a step. So f of x0 plus x1 over 2 times delta x. So that would be the height. This point here is f of x0 plus x1 over 2. What I have done here is I averaged x0 and x1, so add and divide by 2 to get whatever the value is the middle of that interval. And I'm computing function value on that point times delta x. So I have the height. When I compute all of that, I have the height, and then times delta x, the width, and I have the area for the first triangle. So in this case, I will also have x1 plus x2 over 2 delta x plus fx2 plus x3 over 2 delta x plus the last is f of x3 plus x4 over 2 delta x. So now A is given as factor out delta x. You can factor out in front or in the back, it doesn't really matter. We put f of x0 plus x1 over 2 plus f of x1 plus x2 over 2. You can have as many of these as you need. It's not just 4. And that will be the mid rule. Shall we do an example? Of course you want the example. You love examples. Let's do something awful. Integral of square root of x. Let's say you don't from 3 to 7 with n equals to 4. Oh, I don't want 3 to 7. I want 3 to 6. 3 to 7 is going to be perfect. 7 minus 3 is 4. 4 divided by 4 is 1, and then delta x is 1. And I want fractions and decimals and pain and suffering, because that's what the numerical methods are for, right? You'll get square root of 16 when you do the, your U sub problems. So you draw some kind of sketch, and you say we're going from 3 to 6 here, and we have to have 4 rectangles in that region. So the question is, what are these values along the way? Well, when you average 3 and 6, you're going to get 4.5 in the middle. And then you average 3 and 4.5, and you get 375. And you add, you get 525. Awesome. So I'm going to actually draw this larger now so that we can pick our values better. So the first number is 3, the next one is 375, and then the next one is 4.5, and then the next one is 525, and then finally 6 at the end. Now you can quickly compute delta x, because you will need that, which is 6 minus 3 divided by 4, which is 3/4, also known as 0.75, depending on what you prefer. So each one of these delta x's over here are going to be 3/4. Now remember what we are doing. We're going to find the middle, and then draw the horizontal line through that middle. So I need to find all of these averages so I can compute. So let's see, what's the area? Area is approximated by dx, which is 0.75 or 3/4, times the function which averages 3 and 375. So I have square root of 3 plus 375 over 2 plus the square root, the average of 3.75 plus 4.5 over 2 plus the square root of 4.5 plus 525 over 2 plus 525 plus 6 over 2. And as you can see, all of these are numbers. If you are not good with computing, you can just punch all of this in the calculator and you will get a value. Where's your iPhone? Or coffee? So what's the number at the end? 6.34. Good enough? Good. So carefully plug in all of these things in the calculator and then compute. Area should be about 6.34. Now we can compute this integral exactly and then figure out what is the best answer. So I'm going to do that actually on the board because I just don't want to. Next one is trapezoid rule, and I'm going to use the same problem with same limits every time. So we have integral, invisible ink, integral. Does anyone have Apple markers?
I don't think they make Apple markers.
Exactly my point.
Yeah. I mean, I'd rather not have a marker than an Android marker. That doesn't work.
Android markers would work. They will be simply exploding with enthusiasm to produce enough. Right. Let's see what the calculator is going to give us for this. We're going to quickly say, so 2/3, 2 divided by 3 times, open parenthesis, 6 raised to 1.5 minus 3 raised to 1.5 and error. So the calculator gives us 6.3338, let's say 6. That's too much of a precision, but that's you go. There we go. So pretty damn good, right? For something where you did zero integration, zero, right, rules and stuff, you just found some averages and grinded through annoying calculation, which most likely you use calculator for anyway. You can use your cell phone as well and so on. Not on a test though. Great. Oh, by the way, at NJT you get to do all of this by hand. No calculators, no simple, no basic, no, yeah. At 4 times the cost of the course. Welcome. We do pop quiz every class. Trapezoid rule. So midpoint rule, as I said, very simple. Make sure you are finding the average. I don't like red line. No. A trapezoid rule. So we draw a function again. I'm going to exaggerate more this time, like this. And we divide this. I'll divide again into 4 because I'm very original. Yeah. They actually are original. And we will connect the corners. You can barely see it there. What we are doing is we are connecting 2 corners with a straight line. If I am to draw this bigger and more exaggerated, right, like this, and then draw a straight line, so if you zoom in, right, so this is a zoom in. I don't know. Zoom in. This is your delta x. Let's say this is your x2, this is your x3. This is your f of x2, and this is your f of x3 in terms of the height. Those are the y values. I mean, I could have zoomed in like this, obviously, but then, right. So what's happening here? Well, if you take a look, you are creating error, which is the purple part, but it's tiny, right? It's tiny error. And now you will be using formula for trapezoid to come up with the area, because each one of these shapes is a trapezoid. Now, you are used to trapezoids looking like this, and you know they have a height, and their area is the average of the two parallel sides times the height. So this is your A, this is your B, and this is the height. Now you take this trapezoid and put it just sideways. So you're looking into what we call a right trapezoid, right? Looks like this. And just stand it up, but it still has A and B, and look, age. Age is actually delta x, right, when you stand it up. Which quickly tells us what the formula for this is, because each one of these delta x's is age for each trapezoid. So now, what you have here is the area. We usually use T for trapezoid. Tn, n telling us how many rectangles we are using. So this will be T4 actually. Without deriving this for some time, delta x over 2, and now we go f of x0 plus 2 f of x1 plus 2 f of x2 plus dot 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 plus 2 f of xn minus 1 plus f of xn. Observe the pattern. It's 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1. All right, so all the 2's in the middle, and the end ones are single. Now, you can quickly see that from the picture, because clearly for this trapezoid here, you're using x1. And for this trapezoid here, you're again using x1. So you can use it twice. There are certain things that you can, right? And that's over 2 is the factored out over 2 over there. It's very quick to see how this works, right? This formula is extremely easy to derive. So that's what it is. That's the formula. That's the trapezoid rule. So now we get to use it on our problem again, looking for answer that is going to be very close to 6.3. So this is the trapezoid rule. I'll put it on a cloud. There we go. And now we find the integral 3 to 6 of square root of x dx using trapezoid rule with n equals to 4 again. Well, we know that delta x is equal to, just like last time, 3/4, also known as 0.75. We know that much. We know the values for x0, x1, that none of that stuff changed, right? So x0 was 3, x1 was 375, x2 was 4.5, x3 was 525, and x4, the last point, was 6. So now we write T4, trapezoid rule with 4 rectangles, so T4. And we have delta x over 2, so 0.75 divided by 2. And now I have f of x3, so f of 3 plus 2f of 375 plus 2f of 4.5 plus 2f of 525 plus f of 6. Now you know that f of x is root x, so you will have to compute all of those values. So half of 3/4 is 3/8. Well, it's 0.375. And now over here I have a square root of 3 plus 2 square roots of 375 plus 2 square roots of 4.5 plus 2 square roots of 525 plus a square root of 6. Fire up your calculators. So what do we get? Approximate it. Well, no, it's equal. What do we get?
6.32.
Awesome. Right where we need it to be, right? Great. So trapezoid rule, good. We have one more rule, and that is Simpsons rule. Oh, it should be red. Now what Simpsons rule does is filling arches through 3 consecutive points, and those arches are actually parabolas. So any parabolic problem, if you have to integrate any of the x squared, right, situations or functions, you will actually get exact answer. So instead of using straight lines like we used so far for right and left sum and midpoint, we use the straight constant approximation. For trapezoid rule, we again had the straight line, but it was slanted. And now we are moving into actually a quadratic line. And this is where we end the lecture with Simpsons rule. But there is also another rule that you learn later on if you keep taking math courses and you take numerical analysis. You learn something of cubic splines, which is a 3rd degree. We generally don't need anything better than that, because these rules are already pretty dang good, and then that one is even better, and then we really don't need anything better after that. So what's this Simpsons rule? Well, it does the same thing, except it's much harder to draw. So you have some kind of function. That function is going to be again divided into multiple rectangles. You are going to have your points everywhere, and then you use 3 points at a time to fill the best possible arch that you can. Now, I did not draw this arch over the black line. I just kind of wanted you to see. I'm going to go with the purple one actually on top, like this. So this is what Simpsons rule does. It takes the first 3 points, fits the blue line through them, then the second 3, then the next 3, and then we're actually done with the case of this. Now there is one important thing here, and that is for Simpsons rule, n must be even. So if you see on a test, do S5 for a particular integral, you know I'm trolling, right? Can't be done, because you won't be able to set it up. You'll see why. So n must be even. Make sure you know that. Now, just like for the trapezoid rule, we have the pattern for this one. Oh, delta x is still the same, b minus a over n. Doesn't change. N must be even, so don't forget that part. Now, we have our x0, x1, x2, x3, x4. And each one of these is equal length delta x. So now, what I'm going to do is write out S of n, which is now delta x divided by 3. and the pattern is f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus 2 f of x4 plus dot dot dot. So the pattern continues. It goes 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2. And I'm going to have 2 f of xn minus 2 plus 4 f of xn minus 1 plus f of xn, the last point. Again, no coefficient there. So, well, coefficient is 1. Put this on a cloud. This is your formula that you are memorizing. You are memorizing just patterns inside. So what is it? It's 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So if you have 4 rectangles, you will have 5 points, right? Because between 5 points you can fit 1, 2, 3, 4 rectangles, right? So 4 rectangles, 5 points, and here it is, f of x0, f of x1, so 1, 4, 2, 4, 1. The pattern works. You cannot escape this pattern. You must start with 1 and then go with 4, and then alternate 2 and 4 forever, and then end with 4 and then 1. You will see that if you try to do that with odd number of rectangles, the pattern won't fit because you will have a 2, and then you will have a 4, but there will be no more to get the 1. You will have to skip something, and it doesn't work. Again, the same problem. We have the integral 3 to 6 square root of x dx. We are going to do S4. Delta x is still b minus a over n, which is 0.75, also known as 3/4. We have the s of 4 to be equal to delta x, which is 0.75 divided by 3, times f of x0, which is 3, plus 4 f of 375 plus 2 f of 4.5 plus 4 f of 525 and plus f at 6. Which is 0.25 square root of 3 plus 4 square root of 375 plus 2 square root of 4.5 plus 4 square root of 525 plus square root of 6. And now you will use your trusty calculators to give me the answer once you're done computing. What are the numbers? 6.3338. Thank you. Bad. All right. Obviously, the higher the order of approximation, the better the approximation. That is 7.7. Adding, subtracting, multiplying will be of these numbers. There is nothing else in these sections other than you memorizing these formulas and patterns. You are learning this. So in chapter 7, so far, you had to memorize the integration by parts formula. You had to memorize pairing for trig functions and some of those substitutions, the procedure for trig sub, unless you want to memorize the formulas from the textbook. You memorize the 4 setups for partial fraction decomposition, and now you're memorizing 3 formulas here, 4 formulas actually. You have the delta x formula that you should know from Calc1, and then 3 methods that you learned. The midpoint formula, the trapezoid formula, and the Simpsons formula are the ones that you are memorizing. Zero calculus, done in an entire section. If you know the formulas, then you're able to divide properly to add what the correct numbers are. You'll be fine. This is how your calculator works, integration. You have these calculators actually can integrate because there is somewhere, I think, calculator or something has the integral for it. Yeah. So these guys can integrate. Then you have the other calculators. Then you have all the software that's out there on the market. So all of those do this over 10,000 rectangles or so very quickly because those algorithms are well developed. I mean, if you're programming to do any of this stuff, you're technically inventing the wheel because all of this is already there, and it works. But it's a worthy exercise for those of you who are computer science, so you should try to program something like this and make it work. So we'll take a short break, and then we're going to do calculus. Right? What time the class ends? 7:50. Yeah, we have time. Yeah, good. So I'll restart the stream.